Hey guys, today we're going to look at limits that involve infinity. Now, whenever we have a limit that goes to infinity or a limit that equals to some kind of infinity, that means that we're talking about asymptotes on our graph. So first we're going to examine several graphs and find those indicated limits. Here we have the graph of f of x, which is equal to 2x squared, 2x plus 1 over x minus 3. If you're trying to find the limit as x is approaching 3 from the left, as you can see on the graph, at x is equal to 3, we have a vertical asymptote. Because these are one-sided limits, we can actually look on the left side of 3 and we see that the graph is going down forever. Therefore, this would equal to negative infinity. Versus when the limit as x is approaching 3 from the right, we see that it is going up forever, and therefore our answer would be infinity. Whenever you have your limits as x is approaching some number, if it equals to infinity, this is proof that we have a vertical asymptote. And I'll clarify this later on in the lesson as well. Now let's look at the same graph, but now we're looking at when the limit is approaching either negative infinity or positive infinity. This is the equivalent of finding the end behavior of your graph. If I'm looking for the limit as x is approaching negative infinity, we are talking about the left side of the graph here. And we can see that it is leveling out at this particular y value, which is 2. If I were to look at the right side of the graph, same thing, we see that the graph there is leveling out as well at the same exact value of 2. And that's because we have a horizontal asymptote, which affects the end behavior. So these are the limits that you would use to prove that there is a horizontal asymptote. So to break this down, right, we have infinite limits, which is when your limit equals to some kind of infinity. And we use these limits as x is approaching some value c to show that we have a vertical asymptote at that particular x value. Since remember, your vertical asymptotes are lines, they are always written as x is equal to whatever number it is. And if your y values are going to either infinity or negative infinity, that means that we have a vertical asymptote at that particular x. Now, for a limit that's at infinity, meaning that x is approaching some kind of infinity, if you get some number, that means you have the horizontal asymptote at that y value. Remember that your limits, your answers to limits, are the intended y value of your graph. So therefore, if it equals to a number, that is your horizontal asymptote. So now let's look at these limits here. Now we have one-sided limits. So if I were to plug in 2 into this first one, I would get 0 in the denominator, meaning that it could be a vertical asymptote or it could be a whole. It depends. We would have to factor both the numerator and the denominator. So let's look at this first function. 2x squared minus 2x minus 12. I can factor out a 2 from that numerator, leaving me with x squared minus x minus 6. And the denominator, this is a difference of squares, so I can factor that to be x plus 2, x minus 2. This is not fully factored because of that numerator, so we can factor that numerator more. X squared minus x minus 6 is x minus 3 and x plus 2. And this is over x plus 2, x minus 2. So we have the x plus 2's that cancel, and I'm left with the rational function 2 times x minus 3 over x minus 2. At this point, if we could, we would plug in that x value. But if I plug in x is equal to 2, I still get 0 in the denominator. So this indicates that I have a vertical asymptote. Since this is approaching 2 from the left, we're going to plug in a number that is slightly to the left of 2. So let's say 1.9. Now at this point, I already know there's a vertical asymptote, so my answer will be some kind of infinity. When you plug in 1.9, we're trying to figure out what the sign of that infinity would be. If I plug in 1.9 into the numerator, I would get 2 times some negative number. So that would be a negative. And in the denominator, we would have 1.9 minus 2, which would also be negative. And a negative divided by a negative is equal to a positive infinity. So this would be my rationalization for a vertical asymptote. We would say that there is a vertical asymptote. So all of these, remember, prove vertical asymptotes. In the example of A, there is a vertical asymptote at x is equal to 2, and then you would restate your limit, because the limit as x is approaching 2 from the left of 2x squared minus 2x minus 12 over x squared minus 4 is equal to, and you would have to write what infinity it equals to. So that would be how you would prove your vertical asymptote. Now let's do one more example. For B, we have the limit as x is approaching negative 1 from the right of x squared minus 3x plus 2 over 2x plus 2. So we can factor that numerator. When we factor, that would be x minus 2, x minus 1. And then in the denominator, I can factor out a 2, and it would be x plus 1. Nothing here cancels. So that means that x is equal to negative 1, because of the denominator, is a vertical asymptote. Since this is coming from the right, I'm going to plug in something slightly to the right of negative 1. So in this case, I'm going to plug in negative 0.9. Remember that we already know the answer is some kind of infinity. What we're trying to figure out is whether it is positive or negative. So when we plug in negative 0.9, in the numerator, you would have negative 0.9 minus 2, which is a negative, times negative 0.9 minus 1, which is also negative. And then we would divide that by 2 times negative 0.9 plus 1, which would be positive. The numerator would give you a negative times a negative, which is a positive, and if you divide it by a positive, we get a positive infinity. So for this one, you would state there is a vertical asymptote at x is equal to negative 1 because the limit as x is approaching negative 1 from the right of x squared minus 3x plus 2 over 2x plus 2 is equal to infinity. Now let's try one more. We want to find if there are any vertical asymptotes here. And if there are, we're going to justify its existence using limits. For this one, when you look at the numerator, we have 2x squared plus 7x plus 3. Not every term in the numerator is divisible by 2. So we're going to want to use the AC method that we learned in Algebra 2 and continue to use in pre-calc. So remember that the AC method, we take A times C. 2 times 3 is 6. And I'm trying to figure out what two numbers multiply to give you 6 and add to give you B, which is 7. And those two numbers would be 6 and 1. So now I can set this up. I'm going to rewrite that quadratic as 2x squared plus 6x plus x plus 3. I use these two numbers to rewrite B. Once you have that rewritten, then we can factor by grouping. So remember, factoring by grouping is always the first two and the second two. You factor what you can from the first two terms. In the first two terms, I can factor out a 2x, and I would be left with x plus 3. Since I can't factor anything from the second two terms, you can just put plus 1, x plus 3. Now, when you've factored by grouping, these two, whatever is in the parentheses, should be the same, which they are. And that is one of your factors. And then my other factor is what's left over, so that 2x plus 1. And then the denominator, x squared minus 2x minus 8, could be factored by x minus 4 and x plus 2. Now, because nothing factors here, or rather nothing cancels, we have two vertical asymptotes. We have x minus 4 and x plus 2, and if we set it equal to 0, this means that you have the vertical asymptotes at x is equal to 4 and negative 2. Once you have set up, okay, I know what my vertical asymptotes are, now you have to find their limits to prove that we have a vertical asymptote. You can choose whichever direction you want to come from. So let's say for as x is approaching 4, I'm going to choose to come from the right. You don't have to do both. If there's a vertical asymptote, just by showing that one side is equal to some type of infinity, that is proof enough. So we're finding the limit as x is approaching 4 from the right of g of x. Now I chose to write g of x. You can also just copy the function. It's completely up to you. So since I'm finding for when x is approaching 4 from the right, and I know my answer will be some kind of infinity, I am going to plug in a number slightly to the right of 4. So in this case, let's say 4.1. If I plug in 4.1, the numerator would be positive, and then this would be positive, so the numerator overall is positive. And if I plug in 4.1 into the denominator, 4.1 minus 4 is positive, and then when you plug in 4.1 into x plus 2, it would also be positive. Therefore, this limit is positive infinity. So this would be my proof that we have a vertical asymptote at x is equal to 4. Now we would need to show that we have a vertical asymptote at x is equal to negative 2. So we're going to set up our limit here as x is approaching negative 2, let's say from the left this time, of g of x. So if I'm plugging a number slightly to the left of negative 2, I'm going to plug in negative 2.1. Again, I know I have my answer is going to be some kind of infinity. I am just checking to see what the sign would be. If I plug in negative 2 from the left, so negative 2.1, in the numerator we would have negative 2.1 plus 3, which would be a positive number. If I plug in negative 2.1 into 2x plus 1, that would be a negative number. So a positive times a negative would give me a numerator of a negative sign. Then if you plug in negative 2.1 into the denominator, negative 2.1 minus 4 would be negative, and negative 2.1 plus. So when you're trying to find the limit as x is approaching any kind of infinity, what you're really trying to determine is the end behavior of your graph. So there are a few tricks in order to find these limits if you have a polynomial type function. And by finding these limits to infinity, what we're trying to do is determine its end behavior, which we use the leading term test. Now the leading term is the term with the highest exponent, meaning the highest degree. And then what we do is we check the degree and check the leading coefficient, which is the number that is attached to that variable. If your degree is odd, that means that your ends will be opposite. Now the sign of your graph, of your coefficient will determine the right side of the graph. So we can see here that because the exponent here would be odd and that coefficient would be positive, that right side of the graph, so the limit as x is approaching positive infinity, is infinity. Therefore, if they're opposite ends, the left side must equal to negative infinity. Now, if your exponent is odd, again, still opposite ends, but the leading coefficient is negative, then that means that the right side of the graph is going down, meaning towards negative infinity. So since it's opposite, the left side of the graph would go up towards positive infinity. And again, we can see this on the graph. The left side is going up and the right side is going down. For even exponents, when you have the leading term has an even exponent, both ends are going to go in the same direction. So if the sign is positive, that means that both ends are going up towards positive infinity. Versus when you have a negative leading coefficient and the exponent is even, then both ends would be going down to negative infinity. So we can apply this when we are finding the limits as x is approaching some type of infinity for polynomial type functions. So for example, for this first one, We are looking for the limit as x is approaching infinity of this polynomial. So that means I'm checking the right side of my graph. Since this is an even exponent and the leading coefficient is positive, that means that both ends would go up. Since this indicates I'm looking at the right side of my graph, then this limit is equal to positive infinity because the right end would go up. Now for b, we have a polynomial type function, but it hasn't been multiplied yet. So instead of multiplying everything out, because that could take forever, what you do is you take the leading term of each factor. So we have negative x, and that negative x is being squared, times x from this factor, and then times another x from this factor. If I multiply everything together, negative x squared becomes positive x squared times x, which gives you a leading term of x to the fourth. It is an even exponent with a positive coefficient, since it's like that invisible one, so both ends would go up. Now this is the limit as x is approaching negative infinity, so we're looking for the left side of the graph. Since the left side would go up, this means that this limit would approach infinity. For this one here, we have an odd coefficient. An odd exponent, meaning that ends will be opposite. Since the coefficient is positive, that means the right side is positive, meaning that the left side must be negative. This limit is for when x is approaching negative infinity, so the left side of the graph. So therefore, this limit would approach infinity, negative infinity. With this last one here, we have the limit as x is approaching infinity of this polynomial type function. Again, we have an odd exponent, but we have a negative coefficient. So that means that the right side is going down, and the left side, is going up. So since this is for when x is approaching infinity, that is the right side of my graph, and therefore this limit would equal to negative infinity. Now for these in particular, what we're going to do is we're going to learn how to find the limits as x is approaching infinity for rational functions, basically the long way. I'm going to show you the long way now, and then I'll show you the short way afterwards. But basically what you're looking for, like I said, is the end behavior. And when you have a rational function, there is high possibility that you have a horizontal asymptote. So I put steps here for you to follow. When you're trying to find the limit as x is approaching some kind of infinity, you're going to take every single term and you're going to divide every term in both the numerator and the denominator by the highest power of x that appears in the denominator. So for example, here in this first one, the highest power of x would be x squared. So I'm going to divide every term by x squared. So we have x over x squared plus 2 over x squared all over x squared over x squared plus 5x over x squared plus 6 over x squared. And then what you do is you simplify. So x over x squared is 1 over x plus 2 over x squared divided by 1 plus 5 over x plus 6 over x squared. The next step would be to plug in infinity, so to speak. If we plug in infinity, you're going to see that we have infinity in the denominators for these terms here. If you have infinity in the denominator, that will be 0. Because think about what the fraction would equal to. If you're going to have 1 over infinity, that's going to be 0.0000000 forever. Okay, so anything that's over, or when you have x still in the denominator, this is just 0 plus 0 over 1 plus 0 plus 0. So what I end up with is 0 over 1, which 0 divided by anything is 0. So this would be that we have a horizontal asymptote at y is equal to 0. So our limit would equal to 0. And you can see the horizontal asymptote on the graph. So the graphs are here on the bottom so that you can see what happens when we do this process in terms of what it means for our horizontal asymptotes. When we look at the second one here, I see the highest power of x in the denominator is x squared. So I'm going to take every single term and divide by x squared. So 2x squared over x squared plus 7x over x squared plus 6 over x squared all over x squared over x squared plus 5x over x squared plus 6 over x squared. Now I can simplify this. So we have in the numerator 2 plus 7 over x plus 6 over x squared all over 1 plus 5 over x plus 6 over x squared. Now if I plug in infinity, anything over infinity is 0, so these are all 0. So all we have left is 2 over 1. This means that the limit is equal to 2. And we can see the horizontal asymptote here at y equals 2. Finally, this last one. The highest power in the denominator is x. So I'm going to take everything and divide it by x. So x squared over x plus 3x over x plus 2 over x all over x minus 1 over x. When I simplify this, I get x plus 3 plus 2 over x over 1 minus 1 over x. These here are just 0. Now when I plug in infinity, I get in the numerator infinity plus 3 over 1. Infinity plus anything or minus anything is still infinity. So since I have infinity in the numerator and it's over 1, it's still going to be infinity. So what does this mean? The limit, not only as x is approaching infinity, is infinity, but this means that there is no horizontal asymptote. You only have horizontal asymptotes if these limits equal to some real number. Now, as I mentioned, there is a shortcut. Since you are finding limits at infinity, that means that you are trying to figure out those horizontal asymptotes as we just saw in the previous slide. If the degrees are equal from the numerator and the denominator, so that's the shortcut. You're going to compare the degree of the numerator with the degree of the denominator. If they're equal, then you just divide the coefficients that are attached. So 2 divided by 1 is equal to 2. So this means I have a horizontal asymptote at y is equal to 2. If the degree of the numerator is larger than the degree of the denominator, then this will equal to some type of infinity, meaning there is no horizontal asymptote. And if the degree of the denominator is larger than the degree of the numerator, then that limit is equal to 0, and you would have a horizontal asymptote at y is equal to 0. So if you have a multiple choice question, you can use this shortcut. However, if it's an FRQ, you're going to want to show your work using that long way. So which is exactly what I have written here. So for this one, we're going to find the limit of this function. Now, I forgot to write the limit, but what we're essentially finding is the limit as x is approaching infinity of h of x. So if we were doing this the long way, we're going to divide everything by x squared. So 5 over x squared minus 2x over x squared minus 2x squared over x squared all over 3x squared over x squared plus 2x over x squared minus 3 over x squared. When I simplify this, I would get 5 over x squared minus 2 over x minus 2 over 3 plus 2 over x minus 3 over x squared. Anything that has x in the denominator would just be 0 if I plug in infinity. So what I'm left with here is negative 2 over 3. And this would be my horizontal asymptote. So remember, these limits as x is approaching infinity is proof of a horizontal asymptote. And when you would write your justification, you would say there is a horizontal asymptote at y is equal to negative 2 over 3 because the limit as x is approaching infinity of h of x is equal to negative 2 over 3. Now, just as a reminder, right, if I were to use a shortcut, I have to look at the highest degree of the numerator with the denominator. Since they are the same, I would just take those coefficients and divide them. So this would leave me with negative 2 over 3, which is what I found here when I did it the long way. So now what happens if I were to find the limit as x is approaching negative infinity? And most of the time it does not matter, but we're still going to do this the long way and see what happens. So as you can see, right, if I were to look at all of this, my highest degree is x squared. So if I divide everything by x squared, you get 2x squared over x squared plus 7x over x squared plus 6 over x squared all over x squared plus 5x over x squared plus 6 over x squared. And if you simplify this, you would get 2 plus 7 over x plus 6 over x squared all over 1 plus 5 over x plus 6 over x squared. If you were to plug in negative infinity, those fractions would still be 0. Because since a negative infinity, if you divide by a negative number, if you divide, a number by a negative and it's approaching 0, 0 is neither positive or negative, so it doesn't matter. And what we're left with here is 2 over 1, so 2. So if your limit is x is approaching negative infinity, if there is a horizontal asymptote, it will not make a difference. You would still get the same answer as you did if you were to plug in x is approaching infinity. Now, over here in this example, however, let's just use the shortcut, right? I see that the numerator is larger than the denominator. This means that there is no horizontal asymptote. But I still need to know if you're going to have an infinity or negative infinity for the left side of the graph. And since this is not a polynomial type function, I can't necessarily use the leading term test. So what I'll do here is I'm going to think of plugging in infinity into the leading term of the numerator and the denominator. So I'm just looking at the x squared and the x. So if I were to plug in negative infinity, I would have negative infinity squared over negative infinity. What you're looking for here is the sign. Okay, we already know that the answer is going to be some kind of infinity. I just want to know whether it's going to be positive or negative. In the numerator, if you square it, you'll get a positive. And in the denominator, you have a negative. So a positive divided by a negative is negative infinity. And we can see from the graph that the left side is going towards negative infinity. Now, when we look at this particular function, we notice that we have two horizontal asymptotes, which is very rare. And this happens in the case when you have a rational function with a radical, whether it's in the denominator or the numerator. As you can see here, the limit as x is approaching negative infinity, so the left side of the graph, it is approaching negative 2. And the limit as x is approaching positive infinity, it's approaching another asymptote, which is 2. Keep in mind that yes, my function here did cross the horizontal asymptote in the middle. Horizontal asymptotes are not like vertical. Your function can cross it. However, the ends won't. So that's the difference. So now how do I go about figuring this out if I don't have a graph? So here we have an example. The limit as x is approaching negative infinity of 2x minus 2 over the square root of x squared plus 1. When I look at the highest degree in the denominator, what I have is the square root of x squared. Now, if you were to find the square root of x squared, that would equal to plus or minus x. Now, depending on what side it's approaching will determine whether you're going to plug in, or rather whether you're going to divide by positive x or negative x. Since this is approaching negative infinity, I am going to use negative x. So here we go. We're going to divide everything in the numerator by negative x. And then in the denominator, since it is still inside of the square root, we are going to still divide by x squared. So now we simplify this. 2x over negative x is negative 2 plus 2 over x because of the negative and the negative over the square root of 1 plus 1 over x squared. Remember, anything over x will just be 0 when you plug in negative infinity. And what am I left with here is negative 2 over the square root of 1, which is just equal to negative 2, which is what we found in the previous slide when we looked at the graph. The limit as x is approaching negative infinity was negative 2, because this is the same function that we're working with. So now over here, right, again, same situation. We have the square root of x squared as our highest degree in the denominator. And when I square root that, I get plus or minus x. Since this is approaching the right side, I am going to use positive x when I divide everything in the numerator. So we have 2x over x minus 2 over x all over. Now remember, since we're still inside of the square root here, I cannot divide by x because that's when it's outside of the square root. So I am going to divide everything in the denominator by x squared. And when I simplify this, I would get 2 minus 2 over x over the square root of 1 plus 1 over x squared. Again, anything divided by infinity will be 0. And so here I have 2 over the square root of 1, which is equal to 2. Let's look at a couple more examples. So here, the highest degree in the denominator would be the square root of x squared, which again, we already know, plus or minus x. Since this is approaching negative infinity, we are going to divide everything in the numerator by negative x. So 3x over negative x minus 2 over negative x all over the square root of 2x squared. And remember this, we keep the x squared plus 1 over x squared. So now when I simplify, this will give me negative 3 plus 2 over x all over the square root of 2 plus 1 over x squared. Anything divided by infinity will be 0. So here my limit will be negative 3 over the square root of 2. So this would be my horizontal asymptote. So remember, you would say, because this question is asking, what does it say about the presence of horizontal asymptotes? We would say there is a horizontal asymptote at y is equal to negative 3 over the square root of 2 because the limit as x is approaching negative infinity of 3x minus 2 over the square root of 2x squared plus 1 is equal to negative 3 over the square root of 2. Now in this last one, since this is as x is approaching negative infinity, we are going to plug in, or rather divide everything by negative x. So here we go. We have x squared over negative x plus 2x over negative x all over the square root. Now here we're inside, so we still divide by x squared. Now we simplify, so we have negative x minus 2 all over square root of 3 plus 2 over x squared. So this is the only thing that cancels out. Now if I were to plug in negative infinity, I would have negative infinity minus 2 over the square root of 3. Negative infinity becomes positive infinity. And then minus 2 would still be infinity. And if you divide infinity by anything, it's still infinity, especially since this is a positive number. So this means that my limit is equal to infinity. Now what this means is that there is no horizontal asymptote. Remember, for it to be a horizontal asymptote, your limit at infinity should equal to a real number. So there is no horizontal asymptote because the limit as x is approaching negative infinity of x squared plus 2x over the square root of 3x squared plus 2 is equal to infinity. And that's it. Those are your limits at infinity and infinite limits.